Welcome to the Unit 10 guided practice. Let's start by going over a little bit of the academic vocabulary. You'll need to memorize this for your retest. It says define the following terms. pH is the percent of the hydrogen ion concentration. pOH is the percent of the hydronium concentration. Really, those two terms, pH determines whether if something is going to be an acid or a base, and pOH is just the opposite of our pH. An acid, an acid is defined by anything that contributes to the pH of a solution. A base is anything that contributes to the pOH of a solution. A strong acid ionizes completely, means it donates all its hydrogens. Strong base means that it also ionizes completely, and normally it donates all of its hydroxide ions. When we look at an indicator tells us if there is a change in pH. A Lewis acid is defined by the movement of electrons, and it is when an electron is accepted. Lewis base is when an electron is donated. Bronston-Lowry acids are defined by the addition of a proton, so adding a proton, and Bronston-Lowry base is the accepting of a proton. An Arrhenius acid is when it donates a hydrogen ion, and Arrhenius base is when it donates a hydroxide ion. And then our oxidation reduction is when we have a change in the oxidative states. So oxidation reduction reactants is when we have a change in oxidative states. It says how the definition of a base change when considering a Lewis base, Bronston-Lowry base, and Arrhenius base. So a Lewis base is concerned with the electrons. A Bronston-Lowry base is concerned with the accepting of a proton, and the Arrhenius base is donating a hydroxide ion. B, it says write an expression showing that hydroidoic acid meets the definition of an acid. And so for the Arrhenius acid, it's just hydroidoic, and it produces hydrogen ion and an iodine ion. For the Bronston-Lowry, hydroidoic acid reacts with water. It donates its proton to that water, and we have an iodine ion plus creates a hydronium ion. And then when we look at the definition of Lewis, basically it's the same as our Bronston-Lowry, but we would just show the Lewis structures. So we would show the electron movement with showing the Lewis structures. And we would say that this hydrogen goes here and bonds, and that electron goes with iodine. See, it says what determines if an acid base can be classified as weak or strong. The amount of ionization determines if it's weak or strong. Strong means that it completely ionizes. D, make a list of strong acids, strong bases. So just some strong acids, strong bases that we need to know just when we're looking at problems. Hydrobromic acid is going to be a strong acid. Hydrochloric acid is going to be a strong acid. Perchloric acid, our hydroidoic acid, our nitric acid, and our sulfuric acid. And then strong bases are lithium hydroxide, sodium hydroxide, potassium hydroxide, calcium hydroxide, strontium hydroxide, and barium hydroxide. It says E, draw a diagram illustrating the specificity of all three definitions. So what we can say is that we have Arrhenius, we have Bronston-Lowry, we have Lewis. So all Arrhenius acids are going to be considered Bronston-Lowry, and they're going to be considered Lewis. All Bronston-Lowry are going to be considered Lewis acids as well. And Lewis acids, if they just meet the definition of a Lewis acid, would only be considered a Lewis acid. So all Arrhenius acids are Bronston-Lowry acids and Lewis, and all Bronston-Lowrys are Lewis. And mainly for this class, what we use is the Bronston-Lowry definition. Name the compounds below. When we're naming bases, It's just naming like ionic. So this is barium, this is hydroxide. The name is barium hydroxide. We just have to check out for D block metals. We have iron and hydroxides, but since iron is a D block, we have to look. So the overall compound is 0. That means that this hydroxide is -1, but there's 2 of them, so it's a -2 charge for the hydroxide. And then all you do is you don't know iron, so you just put it as X, solve for X, and we know that it is iron 2 hydroxide because it have a +2 charge. When dealing with acids, if it ends in "ide," we change it to hydroic acid. If it ends in "ate," we just put "ic acid." And if it ends in "ite," we just put "us acid." So we see that this is hydrogen cyanide. So we would say, since it's "ide," it's hydrosulfuric acid. Since this is hydrogen and chlorate, it ends in "ate," so we just go chloric acid. It says write the chemical formula for the acid bases below. So we have lithium and hydroxide. So lithium is +1, hydroxide is -1. Bring the ones down, and we get LiOH. We have 10,4 hydroxide. So Sn plus 4 hydroxide -1. Bring that 1 down, bring that 4 down. SnOH 4. So nitric acid, so using the same logic as writing or looking and naming, if it ends in "ic acid," that means that this is hydrogen bonded to nitrate. So hydrogen's +1, nitrate is NO3 -1, so HNO3. And then hydrophosphoric acid, it's hydroic, so we know it's hydrogen, which is +1, bonded to phosphorus, which is -3, not +3. And you bring this 3 down and that 1 down, and you get H3P. Moving on to pH and pOH calculations. When we're looking at this, we go ahead and when we try to find the pH, the equation that we will be using is pH equals -log of our hydrogen ion concentration. Now, since this is hydrochloric acid, it's a strong acid, so this is the concentration of our hydrogen. So all we do is go -log of 0.003. Trying to find the pOH calculations, so we'll do the same thing and go pH equals -log of our hydrogen ion concentration. But the only other step that we have to do is we know that 14 minus pH equals pOH. Work this out using those two equations and see what answer you get there. And then C, it says find the concentration of hydrogen ions with a pH of 3.2. So if we want to find the concentration, we just go 10 raised to the -3.2. That will equal our hydrogen concentration. And using that equation, we will get 6.3 times 10 to the -4th for our molarity. What are the oxidation numbers of all the elements in the following? If it's in its natural state, it's going to have an oxidation number of 0. So iron by itself, that's its natural state, oxidation number 0. Chlorine, that's how it normally is, as Cl2 is a diatomic, so its oxidation number is 0. Now when chlorine is bonded to calcium, it's going to have, since it's in group 17, it has a -1 oxidation number. So we think about this, the overall charge is 0. Chlorine, since there's 2 of them, 2 times -1 is -2. That means that calcium, what does X equal? X is going to have to be +2. Now on this next one, it's a little tricky. The overall charge is +1. And so hydrogen is going to be plus 1 as well, but there's 4 of them, so plus 4 charge plus x. So we solve for x, and it's going to be negative 3, and that is going to be our nitrogen oxidation number. Moving on to redox reaction, it says in the following reaction, what is reduced and what is oxidized? So we see that zinc is going to go from 0 to a positive charge, and our hydrogen is going to go from a positive charge to 0. So oil rig tells us that oxidation is loss of electrons. When you go from 0 to positive, you lost an electron. So zinc is going to be oxidized, and that means that our hydrogen is going to be reduced. It says redox reactions are governed by what conservation law? That would be the law of conservation of charge. And what does redox stand for? It stands for reduction oxidation reactions.